All right, so welcome to my series of video on statistics. In this particular video, I'll be teaching on how we can use graphs to do descriptive statistics, or how we can use graphs to describe data. So we are going to look at the various graphical ways we can describe data. We will look at frequency distributions, frequency histogram, joint frequency distributions, bar chart, pie chart, stem and leaf, line and chart, etc., scatter diagrams. Now, when we talk about frequency distribution, it's a summary of set of data that displays the number of observations in each of the distribution's distinct categories or classes. Okay, so how do we construct a frequency distribution? Now, let's assume a discrete data. When we say discrete data is data that can be counted. So usually discrete data does not have decimals. So this data here, okay, the number of times customers read the daily newspaper. We can't say that in a week they read it 1.7 times. Either they read it once or twice or thrice. So any data that is counted or any data that does not have decimals, extreme decimals, we say that that data is discrete. Let's assume that in a week, 44 customers read it 0 times. 24 customers read it once. 18 customers read it twice, and etc. and etc. So here we have the number of days reads as against the frequency. How do we construct a relative frequency? So to construct a relative frequency, all that you need to do is that you divide each frequency by the total frequency. All right. So relative frequency is simply each frequency divided by the total frequency. Okay. So if you divide 44 by 200, we are going to get the relative frequency. So you do that for all the others and you get these relative frequencies. All right. That's how we come about the relative frequencies. Okay. There's another example. If you want to compute relative frequencies, we have the frequencies here. You sum them, you get a total, and each frequency divided by the total frequency, we have what we call the relative frequency. All right. So some people can display the scores against their relative frequencies instead of doing the normal frequency. The reason is that the relative frequency will help you know the percentage which moves with a certain score. So for instance, if the relative frequency for the score of 0 is 0.3125, it means that 31.25%, okay, of the people have 0 transactions. Here, we can say that 25% of the people have 1 transaction. So relative frequencies sometimes makes it easier to explain what actual frequencies are. All right, that is how we do it. Now we can use the relative frequency to draw a distribution. Okay, so we can draw a distribution where we have the scores or the marks against the relative frequency. All right, we have, so for instance, we can have the relative frequencies here. Then we can have the marks here or the transaction. So transaction of 0 goes with a frequency of 0.3125. Okay. A transaction of 1, maybe 0. A transaction of 1 also goes with a relative frequency of, let's say, 0.25. So we can draw distributions of relative frequency against a transaction themselves. And that is better done usually in using Excel. So there's an Excel approach to do this simply. Now, how do we construct relative frequencies for continuous data? As I said, discrete data is data that is counted or data that doesn't have decimals. But continuous data is data that is usually measured, right? It is measured. What it means is I can assume any value. So, for instance, somebody's height. It can be 5.76352 meters. Sorry, inches or whatever, or feet. Okay, so continuous data can assume any value. All right. And because of that, to do a relative frequency for a continuous data, we have to group them because it can assume any value. Sometimes if we want to do it one by one, like the discrete data, we have a very long table. So because continuous data can assume any value, we will organize them in classes, okay? Or we will group them, all right? So this is where we determine the class size, class width, and the number of classes. So in drawing a frequency distribution table, you must know that the classes shouldn't overlap, all right? Then the classes should absorb all the possible values. Then the classes should have equal class width. Okay, and once the classes is able to absorb all the values, there will not be any empty classes, all right? And this is essentially done in detail in quantitative methods. So these are the steps. We determine the number of classes, we establish the class width, we establish the class boundary, we determine the class frequency of each class, and then we determine the number of data points in each class. So we can have, there's a procedure, okay? There's a procedure for determining class sizes, all right? A number of classes. When you Google that, you can just see. But most importantly, what I want us to pay attention to is that, you see, usually the frequency is plotted on the y-axis, and then the class intervals are plotted on the x-axis. So if your class interval is 0 to 4, we have 4 to 8, we have 8 to 16, okay? What it means is that the width of each class is what? 4. The width of each class is 4. But if our classes are like 0 to 10, 10 to 20, 20 to 30, what it means is that the width will be very large, okay? So the width will be very large. So look at these class sizes. We have 4 here, we have 8, we have 12. So between 12 and 16 is 4. The width is 4. Between 16 and 20, the width is 4. But we can have class width where we have 0 to 30, 30 to 60, and the width will be very large. All right. Now, when the class intervals are very small, the distribution will be very jagged up. Okay. And when the class width or intervals is so huge, all right, that means that the variation will also be too much and it will be too blocky. So normally the class interval or the width should be of a normal size, okay? So the rule of thumb is that between 5 and 20 classes, 2 raised to the power, the number of classes should be greater than or equal to n, all right? And then to find the minimum class width, it is simply the largest value in the figures minus the smallest value divided by the number of classes you wish to have. And as I've said, the number of classes you wish to have should satisfy this rule, that 2 raised to the power the number of classes should be greater than or equal to the number of data that you have, or the number of figures you have. 2 raised to the power the number of class sizes should be greater than or equal to the number of figures you have. Okay. And then I'm saying that each of the minimum class width should be the largest value minus the smallest value over the number of classes. So let's look at these figures. These figures, the highest is 12, the highest is 50, the lowest is 12. So the range is 46. Now you select a number of classes. So you can select that I want to have 5 classes, I want to have 10 classes or whatever. So in this instance, we chose 5, all right, 5. How do we compute the class width? The class width is the largest value minus the smallest value divided by the number of classes. If I've chosen 5 classes, the highest value minus the lowest value, the answer was 46, divided by the number of classes. 46 divided by 5 is 9 point something. 46 divided by 5 is 9.2. So when you run it off, you have 10. So the class width is 10. All right. Then we can now determine the class boundaries. Okay. We can now determine the class boundaries. So we can have 0 to 10. But remember, there's no figure less than 10. So this class will not appear because there's no figure here lesser than 10. So you start from 10 to 20, 20 to 30, 30 to 40, 40 to 50, and then 50 to 60. All right. And this will give us 5 classes. This will give us 5 classes. And these 5 classes will be able to absorb all these figures from 12 to 58. Because between 10 and 20, we have 12, 13, 17. They are 3. Between 20 and 30, we have 21, 24, 24, 26, 27, 27. So essentially, you realize that you should be able to absorb all the figures. Now, sometimes if you want to avoid overlapping, okay, instead of doing 9 to 20, sorry, 10 to 20, we can just do 9.5 to 20.5. It will still have the class interval of 10. Okay, this will still have the class interval of, sorry, 9.5 to 19.5, sorry. This will still have the class interval of 10, but it will not let a figure like 20 overlap. All right, so that is another way we can also restructure the class intervals. So this is the question as I was doing, 10 but under 20, 20 but under 30. So you can also use this strategy so that you don't just say 10 to 20, but you can just say 10 but under 20, 20 but under 30, 30 but under 40, 40 but under 50, then 50 but under 60, so that a figure like 20 will fall here. Okay, it will fall here, but will not fall here. So there's another strategy. You can just say 10 but under 20 instead of saying 10 to 20, so that 20 doesn't overlap between these two classes. So once you do that, you can get the frequencies. And once you get the frequencies, you can find the relative frequency by dividing each frequency by the total frequency. So this is how we do relative frequency for continuous data. We have to first of all group them, and then we can do relative frequency. Now, we can also find cumulative frequency distribution. So that one, we will accumulate the frequencies. For instance, here, the cumulative frequency will be 3. 3 plus 6 is 9. 9 plus 5 is 14. 14 plus 4 is 18. 18 plus 2 is 20. So these are cumulative frequencies. Then we can also have cumulative relative frequency, which is the 0.515 will start, plus 0.3 is 0.45, plus 0.25 is 0.6, plus 0.2, sorry, 0.15 plus 0, that's 0.45, plus 0.25 is 0.7, sorry. 0.7 plus 0.2 is 0.9, and 0.9 plus 0.10, you get 1. So we can also find cumulative relative frequency. Okay, we can accumulate them to find cumulative frequency and then cumulative relative frequency. Okay. So there's an example here which we can go through to find the relative frequency and the cumulative relative frequency and the cumulative frequency itself. The same idea. Again, we can draw histograms with frequency. All right. We can draw histograms with frequencies. So for instance, 0 to 3. So for instance, I can draw, here is 0, here is 3, maybe here is 6, maybe here is 9, sorry. Here is 12, here is 15. So for instance, between 0 and 3, if the frequency is, let's say, 2, I'll draw the histogram like this. Between 3 and 6, if the frequency is, let's say, 4, I'll just go here and draw like this. Okay. Between 6 and 9, if the frequency is, let's say, 6, I'll draw the histogram like this. Between 9 and 12, if the frequency is 4, the bar will look like this. And between 12 and 15, if the frequency is 2, the bar will look like this. So essentially, frequency histograms are used to represent continuous data, because 0 to 3, 3 to 6, 6 to 9, etc. All right. So histogram is not because they are together. That's not why we call it histogram. Histogram is because it is used to represent frequencies of continuous data, or yes, data that is that can be measured, or data that is very continuous like this. Okay. So we can go through these steps and then construct the bars to find the cumulative frequency. You can also do it in Excel. Now, the next graph we talk about is the OGIF. Okay, OGIF. So OGIF deals with cumulative frequencies, all right? Deals with cumulative frequencies. So OGIF, we will just plot the cumulative frequencies against the upper limit. Okay, we will draw the cumulative frequencies against the upper limit. So for instance, if the upper limit is 30, okay, like 30 here, you plot this against the cumulative frequency of this. So secondly, the upper limit of 60 goes with a cumulative frequency of 0.0852. So 60 and 0. So that's it. So whenever we draw a graph of upper limits, or when we draw a curve of the upper class boundaries or the upper limit against the cumulative relative frequency, cumulative relative frequency, it is called an OGIF. So OGIF is simply a curve drawn from the point of upper class boundary, which is plotted against the cumulative relative frequency. Okay, that is an OGIF. Then we also have joint frequency distribution, etc., etc. Now, this is done. Okay, this is done when data is characterized by more than one variable. For instance, if we are looking at payment method as in using cash, okay, a customer can pay for goods. So here, this table shows that 3 customers paid for goods using cash, and those same 3 customers, and then on the other hand, 2 customers or 2 people paid for the parking garage using cash. Okay. So here, cash is the central element, and cash is either being used to pay for goods by customers, or it is being used to pay for parking garage. So whenever data is characterized by more than one variable, like this instance, we can use joint frequency distribution. And it's also called the cross tabulation table. All right. And these are the steps. You can pause and look at these steps to go through how we compute it. It can also be done in Excel. Okay. Now let's go to bar chart, pie chart, stem and leaf diagram. Now, bar chart and pie chart, they are normally used for qualitative or categorical data. Okay. Bar chart and pie charts, they are normally used for categorical or qualitative data. The reason is that if I have male, female, and male, If I want to draw a diagram for this, I have 3 out of 5 in terms of male, okay? There are 3 out of 5 of the total times 360 degrees. This will help me draw a bar chart. The reason is that, you see, for categorical data, we can also only find the number of representations in there. And the number of representations out of the total representations times 360 degrees, we can draw a pie chart, all right? And again, we can just use the representations like maybe male and female. The male, they are just 3, so male is 3, that's somewhere here. And the female is 2, the female bar will look like this. Now, because male and female are not figures, if it was figures, maybe we have 0 to 2, 2 to 4, and etc. You see that the bars will come together like a histogram. But because they are qualitative, you can separate the bars because one bar need not come close to each other because the things down here are not figures, they are just qualities. So bar chart is used for qualitative data, and histogram is used for continuous quantitative data. So the difference between bar charts and histogram is not because one is spaced up and one is together, but the difference is that bar chart is used for qualitative data and histogram is used for quantitative, all right? So let's go into them in detail. So bar chart is just a graphical representation of categorical data in which a rectangle or a bar is drawn over each category or class. The length or the height of each bar represents the frequency, okay, as I've said, right? And the bars may be horizontal or vertical. So here it means that the people who are in the category of general foods is around 160-something thousand, like this, somewhere here. The people who are in the category of food is 136,000, that's somewhere here, all right? Now, because these elements here are qualities and they are not numbers, I don't need to put the bars together. If they were numbers and maybe we move from 1 to 3, 3 to 6, 6 to 9, then the bars will come together when they are representing their frequencies, okay? So that is bar chart, all right? That is bar chart. And then the pie chart, you all know how to do it, is the frequency of that particular item over the total frequency, so frequency of the particular item divided by the total frequency times 360 degrees. And that will help you know the degrees you must draw, okay, the degrees you must draw for a particular slice of the pie chart. So this is very simple, all right? Then also we have stem and leaf plot. Stem and leaf plot. Now for stem and leaf plot, we saw the data from low to high. We analyze the data for the variable of interest to determine how you wish to split the values into stem and leaf. We list all the possible stems in a single column between the lowest and highest values. And then for each stem, we list its leaf. So let's look at these figures. In this figure, the lowest is 78. The highest is 95. So one thing you must know is that usually the first decimal, the 10th decimal place, or this one, the 10th place is usually the stem, okay? And the leaf is the single unit place. So if my highest is 78 and my lowest is 95, it means my stem should be between 7 and 9 because the stem is the 10th place, all right? So we have 3 stems. The possible stems are 7, 8, and 9. So a figure like 78, its stem is 7, its leaf is 8. So there are how many 78s? There's 1, 2, that's 2 of them. Then the 79s are 1, 2, 3. So the stem for 2 78s and 3 79, all of them, their stem is 7. And then for the first 78, its leaf will be 8. Second 78, its leaf will be 8. Then the 79s, its leaf will be 9, 9, 9. All right. So you can do the same for 80. So for 80, the stem will be 8, leaf will be 0. The second 80, the stem will be 8, leaf will be 0. So you can follow through and write all the leaves for this set of figures here. And then we can also do same for the 9. So 9, when we have a figure like 90, its stem is 9, its leaf is 0. Figure like 92, its stem is 9, its leaf is 2. Figure like 95, its stem is 9, its leaf is what? 5. So that is how we plot the stem and leaf. Then also we have line chart and scatter diagram. All right. Line chart is a 2-dimensional chart showing time on the horizontal axis and then variable of interest on the vertical axis. Then the scatter diagram is a 2-dimensional graph of plotted points in which vertical axis represent values of one quantitative variable and the horizontal axis represents value of another quantitative variable. So this is the time, the line chart, right? So the time or the year is on the x-axis, then whatever value we are talking about is on the y-axis. So in 2003, the value was 1,426. So we plot 2003 as against the value of that. In 2004, the value was 1,006 something. So we plot it against 1,006 something. So that's essentially the line chart. Plotting the line and the time against the variable of interest, all right? That's the line chart. So these are the steps that we go through to plot the line chart. And then the scatter diagram is when we plot various plots where each plot consists of an x value and then a y value, all right? So when we have figures like this, we can put volume per day on the x-axis and then cost per day on the y-axis. So when the volume is 23, the cost is 125. So 23 will be somewhere here. And then the cost of 125 will be somewhere here. So this is the plot. Cost per day, a volume per day of 26 goes with cost per day of 140. So 26 will be somewhere here. Then 140 will be somewhere here. So we plot it. So this is the scatter diagram. Okay? This is the scatter diagram. All right. But usually we wish that if there is a dependent variable and there's an independent variable, the dependent variable comes on the y-axis, and then the independent variable comes on the x-axis. Okay, so this will bring us to the end of our series on using graphs to do description of data. All right, so in my next video, I will teach on using figures to do description of data. So I'll see you in the next video. Kindly like, subscribe, comment, and then share. Thank you.